Yeah, so thanks everyone for being here. My name is Giacomo Capodaglio, and I am part of the training team here at AMD together with Bob Roby. And our team at large is going to be involved in this training and not just presenting, but also monitoring the chat channel that we have set up and answering questions. So the AMD presence will be quite large during this event, and hopefully we can answer most of your questions. Yeah, so the training will go on today until Friday included, and let's take a look at the roadmap real quick so that everyone's on the same page on what's gonna happen next. First of all, let me start by asking everyone attending this workshop to help us create a positive environment. We, as the HPC community, are not that big of a group, unlike sometimes we may want to think. So we have to be helpful with each other and respect everyone's path and current career in terms of where everyone lies on their knowledge of computing systems and GPUs. So just please help us set the right tone and be helpful with anyone else that's involved in this event. Okay, so let's take a look real quick at the schedule for this 4-day event training. So for today, we are gonna start with giving you some notions on the programming model for MI200 and MI300 series GPUs. And then we're gonna dive deep into OpenMP offloading. So today, it's gonna be programming model, and then the rest of the day, only OpenMP, starting with an introduction and then going deeper with real world and advanced example. The format of this training is designed in a way that after every presentation, there's gonna be some time that's allotted for you to try on exercises on your own. And this means that we'll be on the call and monitoring the chat in case you have questions or issues, but you are allowed to just explore the exercises on your own, and obviously we'll direct you to the necessary instructions for you to be able to do that on your own. Tomorrow on the menu, we have a long discussion about HIP and ROCm and how to port HIP code and optimize it. And also we'll show you how to leverage the interoperability of OpenMP and HIP. For the next day, for Thursday, Shelby is going to talk about GPU-aware MPI, which is going to touch upon how to basically pass GPU buffers to your MPI calls, simplifying, but you'll see that there's a lot more to it. And then Gina will show you an example that we have created that's intended to be a simple but sort of complete exercise that mimics what a real HPC application could be, because it has MPI, it has halos, boundary conditions, but it's somewhat toned down so that you can familiarize with it rather quickly. And the focus of that is going to be just MI300A, which you will have access to on the AAC. Bob is going to talk about COCOS and then C++ standard parallelism. For the last day, we will talk about the tools, starting from RockGDB, which is our debugger, and then going down to RockProf, OmniTrace and OmniPerf. So the last day is going to be very, very tools intensive, and we're going to show you how to gather information on your application, try to identify what the hotspots are, and hopefully ways you can use to improve your code in terms of performance and make it go faster. Okay, yeah, so that was just a quick introduction on what you can expect from this course. And these are the people that are going to be closely involved in this event. Some of them are going to present during these 4 days, and you can find the emails of any of us, but you can reach us on the chat very quickly. Okay, so let's spend maybe a couple of minutes discussing what is the AAC, the AMD Accelerator Cloud, and how we can leverage it during this event so that you can get on it and familiarize with our software stack and hardware. Yeah, so the first thing that we should probably mention is who to contact if you're having issues for logins. So you can just either email Bob Roby or me, or maybe just even ping us in the chat. That's probably the quickest option. And we will help you troubleshoot any unexpected login issue that you may be having. So no worries, you'll get on it. Okay, yeah, so if you have registered for the event, you should have received instructions on how to log in terms of what's your username and what commands you have to use. If not, please let us know. But the AAC training container is based on an Ubuntu 22.04 system on which we have installed the latest version of Rocka, which is 6.2.1 that I think came out last week. And we have GCC version 11 and Clang LLVM version 17. So your home directory, thanks to some work that Bob has done recently, will be persistent, meaning that if we bring another node, for instance, your files that you currently have in your home will still exist in this new node. So hopefully they're there to stay. And this is how you log into AAC. The username we have provided to you privately via email. And this is just some kind of tip that we share with you to make the login quicker, so you don't have to type the command on the first line. If you include this information on your .ssh/config file, then you can just do SSH AAC and the port number, which right now is 7002. Yeah, so you can copy files from your system to the AAC node and vice versa using either rsync or SCP. Just notice, please, this little detail that if you use SCP, the port number uses a capital P. That got us several times. So just be aware that the P is capital with SCP, unlike SSH that it's lowercase. Yeah, so the container is set up with modules, so you can just get on it and do run a module avail command, and you can see all the modules that we have installed for you. If you're not familiar with the idea of modules, basically you can load a module and that will modify your environment with the necessary environment variables that you would need to run what the module is associated with. And I should say that you know, we have strived to provide you a rich module environment with a lot of software that hopefully can be useful to you for this event, and you will have access to ASC also after the event, so you can experiment. But something that it's worth spending some time on right now is the fact that we were able to include in the container the latest drop of the Fortran compiler. It's called in the container AMD Flank New Beta Drop. But just be aware that this is pre-production software that's not been officially released. So please familiarize yourself with this disclaimer here, which basically means that this is available to you, but you are warned that you are using it at your own risk. So have fun with it, but let that be mindful fun. Yeah, so please, just read this disclaimer and be aware of it. Yeah, so these are just some simple commands to use modules. As I said, you can run module avail and it'll show all the modules that you have available. You can do module load or unload if you want to use it or not use it. You can do module purge, that's going to unload all the modules that you have loaded. And you can do module show, and it'll show you what the module file is, and which means you'll see exactly what environment variables are loaded when you load the module. The node has Slurm installed and running, so you can use slog to get long-term interactive jobs and Spatch. But you can also just run directly without going through using Slurm, which means that the AAC node is not the right place to run performance benchmarks. So just be aware that a lot of users are going to be sharing the same resources. So of course you can run what you want on it, just do not expect to see the same performance that you would see on a node that's been reserved for you to run performance numbers. Yeah, this is just a list of other software that's installed. But I'm sure that as you get on it, you can explore on your own and just be surprised by how much we have there available. So yeah, so this is the introduction. And let me just spend a quick minute to see if anyone on my team is on the call and see if they want to introduce themselves quickly. I'm just going to tell you something very quick about me. I am Giacomo Capodaglio. Before joining AMD, I was a scientist at Los Alamos National Laboratory. My background is in engineering and applied math, and specifically developing applications for computational physics codes. I see that Johanna and Luca are here in the chat, so if you guys want to say something about yourself in this minute that we have left, please feel free.
Yeah, hello, can you see me and hear me?
Yeah.
Great. I'm still getting used to this new tool for video conferences. Hello, I'm Johanna Potyka. I'm in the same team as Giacomo. I'm working from Munich, so just one time zone away from you. I know Edinburgh from student exchange I did in the past, and my background is in aerospace engineering with a major in numerics and computational science. So I'm recently joined this team and work on HPC apps and porting from CPU to GPU using OpenMP. And yeah, I will give the first call, the first overview on OpenMP offload later on.
Thank you, Johanna.
I also recently joined AMD. I'm in the same team as Giacomo and Johanna. And basically, my background is in the computer science. I did a PhD in France, later moved to the center here, Max Planck Computing Center here in Germany, then moved to the industry. And basically, I will be giving a talk this Friday about the GPU profiling tools.
Thank you, Luca. Thank you, Johanna. Okay, so I guess it's time for us to start diving in the actual presentations. Okay. Can you see the new slide deck?
Yes.
Yes.
Okay. So let me start the stopwatch, see if I can respect my time limit. Okay, yeah, so let's dive into the first topic of this training, which is the programming model for MI200 and MI300 series GPUs. Okay, so unlike some people might think, it's now easier to port code from CPU to GPU. And it's not always been this easy, as I'm sure a lot of people are aware of in this event. But luckily, nowadays, we have several tools that we can leverage to make this process easier. Not already easy, but easier. For instance, from the AMD side, we have introduced the APU, the Accelerated Processing Unit, that you have on the ASC available for you, the MI300A. And we will talk in detail during this presentation about what that is and how we can leverage the programming model associated with the APU. But just in short, the APU is a GPU where you have the same memory space for CPU and GPU. And you can already imagine how things are going to be simplified by this, because you will not have to worry about explicit memory management. Additional to this, pragma-based languages can make the porting process quicker, and you can ease into it because with a relatively small number of code lines, you can offload your loop from the CPU to the GPU. So pragma-based languages can be a quick and somewhat soft introduction to CPU to GPU porting. We also have optimized libraries for the GPU that can be used, for instance, to perform some linear algebra operations. And therefore, you don't have to worry about how I'm gonna, do this Fourier transform on the GPU, for instance. You can call an optimized library for that. You can also leverage the interoperability of different programming models, such as, for instance, OpenMP and HIP, as we will see during this event. And now the tools are a lot better and a lot richer, and you have several options that you can use to debug, optimize, and profile your code. So specifically from the AMD side, what we can offer is the APU architecture and programming model from HPC to desktop. And the important point I think here is that the APU programming model does not just apply to the APU architecture, but it also applies to discrete GPUs, such as the MI 210 that you have available on ARCHER2. This means that with the necessary with small modifications, you can run your code that would run on the 300A on the 200 series. And it's not a modification to the code, but just rather a compile flag or exporting an environment variable. So it's easy as that, and we'll show you how to do that. So yeah, so the APU is from AMD is the only product that it's a true APU in terms of having the same memory space for CPU and GPU. And at AMD, we value customer-friendly policies such as open source. Most of our code is open source, and we're not going to lock you in with us as vendors. We do not believe in vendor locking. And also we strive to promote and provide portability for as much as we can. We have industry-leading CPU performance, and we have a real commitment to HPC customers. We know that AI is getting a lot of talk now, but we want to stick around and be available to our HPC customers and be present in the community. Okay, so let's discuss a little bit what are the differences between APU and discrete GPU architectures, even though I kind of already spoiled it a little bit. Yeah, so this little diagram here is making a distinction between compute design and memory design. So the simplest system would have just one compute unit and one memory unit, and it's at the top left of this diagram. But what we are mostly used to working with is what's on the bottom right of the diagram, which is discrete GPUs that have two separate memories, the capacity memory and the high bandwidth memory, and then they have two separate computes for the CPU and GPU. The APU, on the other hand, sits on the bottom left of this diagram because, as you can see from this little cartoon, it has the same memory space for CPU and GPU. And this is really an important breakthrough in terms of what it means when you are programming it and also when you are porting your code from CPU to APU. So from a historical point of view, what somehow stopped the APU from existing sooner, let's just say that, was that there was not enough physical space in the silicon to add the necessary compute capability. However, that changed with the introduction of the chiplet technology that instead allowed to expand this compute availability. So you see that basically in this hypothetical APU with chiplets diagram, the chiplets can be used to add GPU memory, but also CPU memory. And that's the case, for instance, for the APU, where we have GPU and CPU on the same space. But in case it's the requirement is to have even more compute, then you can place all GPUs in your memory space. And that's the case, for instance, of the MI300X architecture. And you can tell that the ability of mixing and matching in a way gives AMD the option of creating new products rather quickly, thanks to the chiplet technology. Okay, so for what concerns the APU programming model, you may already be familiar with the terminology of host and device, but basically the host refers to the CPU and the device refers to the GPU. The CPU is the host because it's in a way hosting the GPU, since the kernels are launched from the CPU. And if you are familiar with C++ or Fortran, host code usually has that type of syntax, whereas device code uses a C-like syntax if you're using HIP, or there are specific OpenMP directives for Pragma-based languages. And for host code, there is only one entry point, which could be the main function for C++ or the program for Fortran, whereas device code has multiple points of entry, which are the kernels. So when programming on a GPU, it's important to be aware of what the memory model is. And the memory model is defined as the rule for the synchronization of memory modifications between threads, compute hardware, and cache. Obviously, it's important to know what the rules of the memory model are, because you want to avoid problems such as race conditions or working with memory that you think has been modified or you think it has not been modified, when actually the opposite has happened. So for what concerns the MI200 series GPUs, these are discrete GPUs, and as this little diagram here shows, they have separate memory spaces. So this means that the memory management has to be taken care of. And that can be done in two ways, either directly, explicitly by the programmer, and by that I mean calling functions or API routines that take care of memory allocation and movement and copies, specifically copies and movement. Or you can do that through the operating system, which we refer to as a managed memory approach. Managed memory just means that the operating system is managing it for you, so you don't do it explicitly. And there are a couple of ways to enable managed memory. And just be aware that the MI200 GPUs have managed memory implemented, and specifically the one you have on ARCHER2. So one way to do that is by exporting this environment variable called HSA_XNAC and setting it to 1. So XNAC is defined as the ability of AMD GPUs to retry memory accesses that fail due to a page fault. So when you export HSA_XNAC and set it to 1, you're basically telling your GPU to move the memory for you. So the code that you have written for MI300A will also run on discrete GPUs. But be aware that the performance will not be the same. It will run, but the performance will be different. The other way, different from the environment variable, is to set a compiler flag. But first of all, you can check that XNAC is enabled on your hardware just by running info and then grabbing on XNAC. And then you can append this this line here, this XNAC plus if you want to enable it, or minus if you want to disable it, after the GFX model when you specify the offload architecture at compile time. Okay, so you know, this is just a diagram that once again reiterates the fact that the MI300A has one memory space for CPU and GPU. But let's take a look at what it means in practice when we have a code that exists on the CPU and we want to move to the APU. So let's start with OpenMP and Fortran. For C++, it's similar, and I'll show you a snippet next. But let's assume that you have some CPU code that allocates some memory and then does some work on it, and then you know, does something else with what you have obtained. So we are using a color coding here to somehow make more explicit the parts that are most relevant to this discussion. And the compute kernels are in orange, synchronization barriers in blue, and explicit memory handling is in yellow. So you see that for the CPU code, you're only on the CPU, so you don't worry about the GPU. There's no memory management. For discrete GPU, you have to explicitly call this OpenMP directive that will move your memory from the CPU to the GPU. And that can be costly in most cases. On the other hand, on the APU, you see that there's no yellow here. You don't have to do that, provided that you include this special directive, which requires unified shared memory. And that's gonna handle it for you. You don't need to worry about the explicit management. For what concerns heap, and I apologize if we talk about heap today, because the talk about heap is tomorrow, but for now, just think of heap as an AMD API that you use to work on GPUs, basically, very broadly speaking. This is a C++ example because heap works with C++, and with Fortran, it's only possible with C bindings. So with Fortran is a bit of a different story. But focusing on C++ right now for heap, once again, we have CPU code on the left, discrete GPU at the center, and APU on the right. And if you look at the discrete GPU code in the center, you see that we are allocating memory on the host, those in_h and out_h arrays. But we are also allocating memory directly on the device with that heap malloc call. So basically, heap malloc is doing the same as malloc, but on the device. We are now initializing the memory for the host array. But then, before we can actually call our kernel, we have to copy the content of the host array to the device array, because the GPU kernel needs memory on the device. So we are making this copy with heap mem copy, running the kernel, calling the synchronization barrier, and then copying back the memory from device to host. With APU, you see that there's no yellow, no green, because once you have allocated the memory on the host, you can feed directly that array to the GPU kernel, and the GPU kernel is going to see it. So you can see right off the bat that the APU code is a lot simpler than the discrete GPU code. The last example is an example that somehow is meant to show you what happens with different frameworks across the APU. So the first panel here on the left is again OpenMP, but for C++, and you see that it's similar to what I already showed you, because we are including this requires unified shared memory directive up here at the top. And Raja and Cocos, we're gonna talk about them in the next presentations, but these are languages that have been developed by two national laboratories in the United States, Lawrence Livermore for Raja and Sandia for Cocos, but they are in a way community efforts. So several other institutions such as AMD have contributed to them. And the idea of Raja and Cocos is that basically you are supposed to have the same source code for GPU and CPU. So they're intended for you to write one code that will run on CPU and GPU. And here you see that the kernel launch has its own syntax for either Raja or Cocos. But once again, you see we're not doing any explicit memory handling for either of them. Okay, so in terms of what are your options, well, there are several options that you can leverage in terms of programming languages that go from native or low level, such as HIP, as we'll see tomorrow. There's options for Pragma-based languages, and the one that we support the most is OpenMP. We have performance portability frameworks, such as those that I just mentioned. And we also have C++ standard parallelism. For what concerns OpenMP, that's what we have the primary support for, and we encourage our users to use OpenMP over OpenACC when possible. OpenMP is implemented through LLVM, and it's implemented in the Cray compilers. So OpenMP is, in a way, what you can do to kind of ease into CPU to GPU porting, because with only a few lines, you can obtain GPU offloading, although the performance will not be as good as when you are using HIP, for instance. So HIP is the low-level language that we're going to talk about tomorrow, and it's a little bit more involved than OpenMP, because I mean you've seen it from the simple examples that we showed before. There are you need to be a little more careful about how you implement with HIP. But the idea is that with HIP, you can get best performance. So if you really want to stick with OpenMP, save HIP for the hottest loops in terms of the ones that are taking the most time, so that you can get very good performance on those. If you're familiar with CUDA and you already have the CUDA code, we have tools to hipify your code into HIP. Basically, there are automatic tools that will just get your CUDA code as input and produce as output a code that has HIP calls instead of CUDA that you can just run on AMD GPUs. And we'll talk about that too next. Just be aware that for the AMD architecture, wavefronts have 64 threads, whereas the warp size for NVIDIA is 32. So this is one of the major differences. For what concerns higher level performance portability languages, we have already talked about Cocos and Raja, and we're gonna go in more detail especially on Cocos in one of the upcoming presentations for this event. Let's just say briefly something about C++ standard parallelism. So with the release of ROCm 6.1, standard C++ standard par is available for AMD GPUs. However, with the 6.2.0 release, something broke. So unfortunately, in the ROCm version that we have on the container, C++ standard par is not enabled. But if you have a way to experiment with version 6.1, then you can turn it on by using the -- ship std par compile flag. So it's a very inviting framework to try out, but consider this option, for experimental use and if you are somewhat experienced with C++. Okay, yeah, and we also have support for other languages such as Python, SQL, and Julia. We have instructions on how to add Julia as a module. And we also support, for the most part, out of the box, several popular machine learning and AI frameworks such as PyTorch, JAX, and CuPy. And you can check out the ROCm GitHub page to see basically AMD implementations of these frameworks that are intended for you to make it easier to use these frameworks on AMD GPUs, even though, as I said, most of them will just work out of the box. Yeah, so I think now it's time for the exercises, and obviously we would be able to answer questions in the chat, but for you to try the exercises, just log into the AAC and clone this repo here that has all the exercises that we're gonna go over during this event. And basically the top level README of this repo has a table of contents of each of the topics that are covered. So you can just click on it and it will take you to the relevant code and instructions. For this specific talk that I just gave, the exercises are located in the managed memory directory, and instructions on how to compile the exercises and run them is in the README file. So for this training event, we have decided to not give you any PDFs, but rather just point you to the relevant READMEs on the GitHub repo, just because it's easier for us to keep track of anything that needs to be updated, and we don't have to, if anything in the future changes, you still know where to find everything, and you don't have to look at a PDF and maybe incurring something that's outdated. So yeah, so this is the end of the talk. Thank you for listening. I'd be happy to talk to you if you have any question, or we can be online here until the next presentation that will be given by Johanna at 2:10 your time. But there's a break at 2, so you can either continue working on the exercises until 4:10, or just enjoy your break. But I'll be on, and my team members are also monitoring the chat, so feel free to contact us either here or in the chat. Thank you. Okay, so for the next talk, we have Johanna, who is connecting from Munich, as she said. And this is gonna be the first talk to cover OpenMP offload for today. And Johanna has recently joined AMD, and she's been a great addition to the team. We're so happy to have her. And please, Johanna, take it away.
Yeah, hello everyone. I think I introduced myself before, so no need for that to repeat it. So we will jump right into the topic, Introduction to OpenMP Offload on AMD GPUs. So I first want to acknowledge all the colleagues who had to prepare those slides which will follow, and we would go through a following agenda for this talk. I will show you the next about half an hour why we want to use OpenMP Offload, and then what compilers are available to use OpenMP Offload, how you can offload. I show this by a simple example. Then we will talk about the device execution model, offload basics, and how you can exploit parallelism on the GPU. So why do you want to use OpenMP Offload? So I assume many of you are familiar with OpenMP and have worked on OpenMP on CPUs before. So something like you see here in Fortran or C, where you parallelize a loop with multiple threads on the CPU is something which you are probably familiar with. So why do you want to use OpenMP for porting to GPUs? One reason may be you already know OpenMP. And the nice thing is that OpenMP is standardized, so it's portable between different architectures and compilers. And as Giacomo also already mentioned, Fortran is supported. So as mentioned before, many HPC codes already have OpenMP and MPI hybrid parallelization. So porting may require only very few changes, and it's very easy to learn some additional OpenMP pragmas and clauses for porting. So I assume, as I saw from the participant list, you're from a wider field of different engineering, physics, applied mathematics applications, and you're interested in results of your application running on a large system and not porting forever. And there, OpenMP is a very convenient choice to port your application with decent performance and also a decent time to get your porting done. It's also interoperable with HIP and the ROCm libraries, so you're very flexible because you still have the possibility to add some HIP in kernels where it might be a bit challenging to do it with OpenMP, but we already see very good performance in many kernels with using OpenMP Offload. And another motivation to use OpenMP is you can compile the exact same code also for the CPU, so you can start porting before even having access to GPUs, and you can also do some correctness checking and so on already on your CPU, even on your laptop at home. And that's sometimes very convenient that you don't have to spend node hours for simple validation checks you can do at home. So as you probably know, OpenMP is an industry standard. Currently, OpenMP 5.2 is available and step-by-step implemented in the different compilers. Online, you can also find a reference guide. I really like that to have it always close at hand if I'm OpenMP programming as a kind of cheat sheet. And there also, if you don't understand what the standard says, there's also examples you can always have a look at and understand better what's meant. So that's really great that OpenMP is also well documented. So what different AMD compilers are available to compile for AMD hardware? There are two major kind of strands of compilers you can use, either LLVM-based compilers, as Giacomo also told you in the last talk, you can compile HIP with HIPCC or OpenMP offload and C programs with AMD Clang. And you can also get some pre-release features in AOMP, which are not yet in the ROCm introduced, so that you can profit from features early on. There's also GCC-based compilers, so GNU compilers in the more recent versions. There's offload to MI100 and MI200 series. MI300, I think it's not yet implemented. So you can have a kind of a functional support in part with GNU compilers, but the primary support is for LLVM-based compilers, which are also developed by teams within AMD. So, and what Giacomo already told you, we have now, it's very new, the compiler is available since yesterday. So you have the first access for this beta release and a pre-release to this new AMD Fortran compiler. So you have a preview for this. It's not yet available for everyone. And it is installed on ASC6, where you're working on for this training. You can module load this AMD Flang new beta drop module and use AMD Flang new for compilation. So this is very great that we can get your feedback on the new compiler. You can get experience with the new compiler. It's a fully functional OpenMP offload compiler for Fortran, and everyone who is working with Fortran, I really recommend you to do the Fortran exercises. We just tested and put together yesterday when the compiler was released. So how do you not only compile for the GPU, but how can you offload an application to the GPU? So first, some compiler flags. I have to do that first. How do you compile? Actually, how do you include that in the makefile? You have to add FOpenMP, like for any OpenMP program, and specify the offload arc additionally. And there are the different choices. In this training, you will use GFX942, as we have MI300A available. On ARCHER, I believe you would use GFX90A for the MI200 series. It's also possible to compile this program. You will now in the next few slides learn how to program the GPU. You can also compile it for the CPU with this a bit lengthy flag. So in the makefile, you may include it like this. I won't dwell on it longer because you can explore it also later in the exercises. In the examples, you will find them also in the training examples repository, like Giacomo already mentioned. There's a subfolder, Pragma examples, OpenMP, and there's C and Fortran exercises in there with readmes, and you can later on try them after this presentation. Sure, you can also use CMake instead of a simple makefile. Especially if you have a logic code, that's probably what you have implemented. And also there you only have to care about FOpenMP, which is maybe already in there if you have a CPU OpenMP code already, and specify offload arc for to fit your architecture. In this case, this example is for MI300A. So I already mentioned it before. It's possible to compile the GPU code for CPUs. This is convenient for early porting and functionality checks without having to use a large system. You only need to remove the offload arc and replace it by this flag I show you here. have a compiler which supports OpenMP 4.0 or greater. And this is really, really helpful because you have only one code which can run on CPUs and GPUs, and you can do debugging also, at least for some functionality checks on CPUs already. There's also the possibility that you accidentally run your code on the CPU. As I told you, okay, you'd simply only have to remove the offload arc flag, and then it still compiles somehow. So you really want to check if you really run on the GPU. And you can do this by either checking ROCm-SMI on the same node where you're running your code. This will show the GPU activity. And the other possibility is that you export libOMP target info equals -1 before you run your code. Then you see what the compiler actually does with data movement and so on to the GPU. Or there's a possibility to use functions from OpenMP to ask if you're really on the initial device. The initial device is the CPU, which is a bit confusing. So there are different possibilities to check in your code at runtime where your code actually runs. So now you're probably very curious. We can compile it, but we still don't know how to program it. How do we do that? In OpenMP, there's the device model implemented since the version 4.0 of the OpenMP API definition. So in the device model, there's the traditional host where you can do multi-threading, like you know from OpenMP on the CPU. And then you can have multiple accelerators or co-processors of the same kind for offloading. Devices are accessible also through an ID. If they are more than one, then you can also specify on which exact device your code has to run by specifying an ID. But for this training, you will not need that. The OpenMP device model doesn't say it has to be a CPU and a GPU. It only says there has to be some host. In our case, it will be a CPU that sends data to a device, and this device does some computation. In our case, it's the GPU. But in principle, this can be any host-device combination, which is able to do what the OpenMP standard says. So now we want to offload to the GPU. So we start our program on the host, which is the CPU. And then we introduce with OMP target that we want to do something on the target, then map our arrays we are using to the device and back from the device at the end of the computation. So you specify everything in the beginning of your so-called lexical scope, do the computation in between, and then your memory is copied back to the device. So it was supposed to be an animation where the data is moved to the device and back from the device, and we show this step by step, but I think this presentation tool doesn't allow it. So imagine with OMP target, we say, okay, we now want to do something on the device. Then we have the map to, which moves the data from this host over to the device. And with the map from at the end of the OMP end target, it will move all the data back to the host. But we will follow this step by step in the next few examples. So first, we focus on the offload basics. In the following, we will have this running example throughout the whole presentation. A simple SAXP, you probably know this. It's a computation where we multiply a scalar with a vector and add another vector, and and the result is written to the same vector we add at the end. So this is something which you would usually do through a library. So don't do this at home. It's just a simple exercise example here because it's very convenient and easy to understand how to do the offloading there. But a library will do that in a more optimized way than we can do this with a few lines of code we can show here on a slide. Okay, so how do we get the computation to the device? In this introductory slide, I already mentioned that we use Pragma OMP target to say, okay, the next thing should happen on the device. Then what does the compiler know about what's coming next? It checks if I'm using some vectors and arrays or other variables inside my so-called kernel, which is running on the GPU, and automatically identifies the variables I have to use and copies those arrays to the device. And after the computation is done, it copies it back from the device. Also, in this case, where it's done automatically, the memory copying, it copies all the arrays we are using from and to the device. So it automatically does something like a map to from for all the arrays. In this case, I only have an example for the Y, but it also does this for the X. But the compiler is also able to check if this array is already there on the device, so it doesn't do unnecessary copies. But what happens is we still have this X copied back to the host, which we do not want. So to get rid of this copying back of the X, which is not necessary because it is not updated inside this computation, we say only map to for the X and to from for the Y because the Y result is changed. And then we only get 2 memory copies from host to the device and 1 memory copy of the Y from the device to the host after the computation. So thing you have to be careful with is if you use pointers. The compiler cannot see how large this pointer may be. So you have to pass the size also to the map clause that the compiler does know how much data has to be copied. This is important, especially as it's used much in C. So now we know how to shift the data to the device, so the GPU and back. As Giacomo said, on the APU, that's not even necessary. But we only use a very tiny fraction of the hardware to do the computation. We want to improve that. So we now want to exploit multi-level parallelism to use the full device, so the full GPU. This is intended behavior, so OpenMP separates offload and parallelism, so the programmer has a lot of freedom how to do it. In theory, any OpenMP construct can be combined to be used with target, but there are only a few which really make sense. For example, I/O is not possible on the GPU. So how do we get more parallelism into the computation? So we still have our OMP target, so we compute on the device, and then we add, like you know from CPU programming, Pragma OMP parallel for SIMD. So we now create a team of threads to execute a loop in parallel, and we also may use SIMD to improve the parallelism. Okay, so we now use a full compute unit on the GPU, but it's still not much better because there are a lot of compute units which are still idle. So how do we improve that? For that, OpenMP offers the teams construct. With teams, we now have multi-level parallelism. So here it's still the same code like before. We have the Pragma OMP target. Okay, we compute on the device, and then we add the teams, our mapping, and then we have 2 nested loops. The one loop is offloaded via Pragma OMP distribute, and the next one has the creates more parallelism by a Pragma OMP parallel for SIMD. So now we use the full device because our OMP distribute all of the different teams now is activating all the compute units. That's great, but you saw this code is now a bit lengthy compared to what we had before. So what is possible in OpenMP is just have everything together in one line, and you can forget about introducing this nested loops. That's just for your understanding that the computation is parallelized on 2 different levels, but for convenience, you can put everything on one line, and this makes it quite convenient to port both in C and Fortran from CPU to GPU. So now we know how to do a computation on the GPU, but what is also important is that we have to optimize how data transfers are done, because the bandwidth for the host memory is hundreds of gigabytes, the bandwidth of the accelerator memory terabytes per second, and the connection may be tens of gigabytes per second. So it's can be very time consuming to do the computation. So unnecessary data transfers must be avoided on a discrete GPU where we don't have a shared memory. So the following, what I tell you now, applies to discrete GPUs on APU. I will mention that later on again. This is not important. So for discrete GPUs, it's important that we use Pragma OMP target data. So this will create a data environment here around all of the computation. On the left side, you see that there are 2 different kernels, zeros and compute kernel, and another compute kernel too, and Saxby kernel called. So we can do a lot of kernel computations on the GPU before even copying back the data. So that's great. So we have the data living on the device for a longer time. And inside the kernels, you do not need the map clauses, so that's also convenient for programming. So there's also the possibility, instead of having a large data region, that you can use unstructured data regions by using Pragma OMP target enter data and target exit data. In principle, it's similar to the data region, just that at the end, you either map back to the host or destroy like a free or deallocate in Fortran, you delete your arrays on the device. This also allows that we have target update in between, that if we have something happening on the CPU with the same data, but we still want to keep a copy on the GPU or the other way around, we can have target update from and to move the data. So here's an example. We have this mapping to the device, and then we can have target update in between 2 kernels, because we may want to do something on the CPU with the data. Like, for example, print the data because we want to do debugging or something like that. So this is a slide you already saw before, and this is what Giacomo has presented already, so I can go over this quite quickly. But now you know what's really behind this discrete GPU programming model compared to the APU programming model. What is important, the important difference is that we have to do all the data mapping, which can be quite involved for a larger app. For such a simple example, which fits on one slide, you think, okay, I can do this 3 lines of code and think about the mapping, but sometimes it's really hard to see where data has to be copied from and to the device. So you can also explore this later in the exercises where you have to look out for and where the pitfalls might be. So on the APU, you don't need all the data copies. So in case you only work on MI300A in the future, you can just forget about everything concerning data mapping. Just put OMP requires unified shared memory on top of every module you write or every program, and then you don't have to care about data mapping at all. And that's really convenient for porting from a CPU to a GPU. So how does it look like if you have a CPU code which is already OpenMP parallelized? So in this case, we have a Fortran example here to have a bit of variation of Fortran and C. You just have to add this OMP requires unified shared memory, what I just mentioned. And the only difference you have to introduce in your kernels is that you have to add target teams distribute between your first OpenMP, Pragma, and the parallel do. You may want to use a collapse if you have nested loops and so on. That's very similar to the CPU. You just have to add these 3 words in most cases, and your porting is ideally done. Yeah, sure, there can be some pitfalls, like things you can't do efficiently on a GPU and so on. So you may have to adapt your algorithm, but an initial port is quite easy. No data management is required on the APU, so you don't have to think about it. To enable this, you have to set export HSA xnec equals 1 before running your application. And then your OpenMP CPU to OpenMP offload porting, that can be really like a find and replace job almost. And that is very convenient with the APU programming model. So to review what we learned so far, to move the computation to the GPU hardware, we use target teams distribute. And then to parallelize the computation, we use parallel for or in Fortran do, SIMD, like on the CPU when you introduce parallelism. There are 2 types of data regions, either a structured block with target data or maps for each individual kernel. And you can have unstructured data regions with enter and exit data, and important also update. I didn't put it on the slide here, but update is also important if you want to make use of this unstructured code regions data management. For the APU, you can forget about data mapping and use OMP requires unified shared memory. You activate it by export HSA xnec equals 1, and you have the possibility with export HSA xnec equals 1 also to use the discrete GPU code, like I introduced you to with the mapping. But if you have export HSA xnec equals 1 enabled, it automatically removes all the data mapping. So you can write or use discrete GPU code on the APU and make use of the APU that it has a shared memory at the same time. So in case you're developing discrete GPU code on the APU, there's also the possibility to have to enforce a discrete GPU-like behavior by setting export HSA xnec equals 1. Then it will do the memory copies like on a discrete GPU, but yeah, from shared memory to shared memory, which is a bit ridiculous. But in case you want to write portable code, it may be a cool feature that you can test also for discrete GPUs with only an APU available. And the main help with this APU programming model is you can port easily to the APU with unified shared memory. And in case you then want to extend it also to discrete GPUs, you can then export HSA xnec equals 0 and do a port which is more universal. So to sum up, we have different compilers you can use for compiling for GPUs and the APU by AMD. So there's very good support for C and C++, and it's already used in many applications, especially in engineering and yeah, natural sciences, where you're focused on getting your code running and not investigating performance for all time. Then we have basic support for Fortran offloading in ROCm, and as we announced, there's active development underway, and you have the possibility to be the first training group who's able to use AMD Flang New in this training, and we are very excited about it to get your feedback on that. The experiences are with the training examples. So OpenMP is backed by an industry standard, so it's something which is portable across different compilers and architectures. And you can seamlessly integrate it with multi-threading on the host. And I already mentioned it, you can use different languages, you can also mix it in different codes, or in the same code, and it's interoperable with, for example, HIP and libraries using HIP, but this will be also the focus of other presentations. So now you can try everything yourself by checking out the exercises. I hope most of you already got access to AIC. And to start with the Fortran examples, you can go to the Pragma examples folder. There's a README with instructions. In the first section, there's the introduction to OpenMP. There are the C instructions and the C code you can find in the respective folders. For Fortran, we have separate READMEs, but this is also mentioned at the top of the first README. So for this exercise, you can start with the Pragma exercises README and follow the instructions. And if you want to test this new Fortran compiler, I really recommend you to check this Fortran README and follow the exercises. There are probably many more exercises than you can do in the next, I think we have about half an hour, including a bit of a break, to do the exercises. So in case you have problems with the exercises the next days, you can also reach out through the MetaMouse chat, and I try to fix your problems. So thank you, everyone. In case there are any questions, feel free to unmute yourself, write in the chat, reach out through MetaMouse chat, however you like it.
Thank you, Johanna. That was a great presentation. I am working with some of the attendees on AAC access. I think most of them got it, but I think we need to get access to a couple more people. But as Johanna said, we are here. If you have questions, and I see that Sam has been answering some questions in the chat. So please either unmute yourself and ask here, or maybe even better, type it in the Mattermost chat so that you can leverage the expertise of also AMDers that are not currently in the meeting, and we can also keep track of your questions. Next presenter will be Shelby, who will talk about more OpenMP coming up at 3:10 your time. Okay, welcome back, everybody. Next up is Shelby Lockhart. Shelby, do you want to take 1 minute to introduce yourself before your talk?
Yes, sure thing. Sorry, I was trying to navigate the video and audio. Hi, everybody. I'm Shelby Lockhart. I'm on Giacomo and Johanna and everybody else's team who's presenting here from AMD. I specialize in scalable solvers on large-scale systems and communication, so MPI, but I am also pretty well-versed in OpenMP. So I'm going to give you guys a talk on OpenMP today, and then I'll give a talk about GPU-aware MPI later in the week. So yeah, pretty excited to be here.
Thank you, Shelby. Very happy to have you. Yeah, so if you're ready, you can take it away.
Okay, sounds good. I think you can see this pointer, so I'll try to use
Yeah,
that throughout the talk. Okay,
we
awesome.
can see it, yeah.
So you were just given a really great introduction to OpenMP by Johanna, and so now I'm going to talk about real-world OpenMP language constructs, and what we mean by that is things you'll probably see in practice or run into if you're after your initial port of a really complicated code and you need to get more performance out of OpenMP. So what does it actually look like? What do the constructs actually mean? What are they doing? Things like that. Okay, so this talk has evolved many times, right? It's a continuous collaboration between multiple data center GPU colleagues. So just a shout out to everyone that has helped make these slides. And in general, what we're going to do is we're going to do a quick review of those OpenMP offloading pragmas that Johanna just talked about, maybe talk about them a bit more explicitly, what they mean, what they're doing, reductions, device subroutines, asynchronous offloading, and then we'll look at a quick case study for NWChem. So this was one of our team members who was actually porting and working on an application code and how they actually got better performance using OpenMP and the changes that they had to make. Okay, so first, and I think this will address one of the questions someone had asked in the chat, a review of OpenMP compute constructs. So whenever we want to compute on the GPU with all of the threads and work groups, we have this pragma OMP target teams distribute, right? That just says distribute the work across the threads and the work groups on the GPU. If we want to parallelize a for loop, we can use a pragma OMP parallel for SIMD, or we can combine these things into one line and have a pragma OMP target teams distribute parallel for SIMD. So compute on the GPU with all threads and work groups, and then parallelize this for loop across those work groups or threads. So a note on this SIMD construct, which was the question that someone asked in chat. This can be dropped in most cases. So a lot of compilers don't actually use this SIMD clause to vectorize. They already are making those optimizations. They don't need to be told to do it. So the SIMD clause doesn't do anything with the AMD OpenMP compiler. It also doesn't do anything with the NVIDIA compiler. So it can be dropped for those two cases. Cray used to use it, but they're also moving to drop it, but Intel still uses it. So if you're porting your code for portability purposes where you want to move it around to different machines, and one of those machines uses Intel GPUs, then maybe you keep it around. It might be dropped by all of them eventually, but for now, it's probably safer just to keep it there, even though in most cases, it's not doing anything. One note though, even if you keep it for portability reasons, it will cause warnings, at least with the AMD compiler. So you might get some warnings that things aren't getting vectorized during compilation, but it's just because it's already making certain optimizations. It doesn't need to be told to vectorize explicitly. So you can ignore that. And then of course, another compute construct that we see fairly frequently and we'll review is this reduction clause, which the syntax is simply reduction, whatever operation we're performing the reduction across, and then the name of the variable. Okay, so some other compute clauses to keep this review going. The loop clause was added as a simpler option that gives the compiler a bit more freedom in how it's going to implement the parallelism for a for loop. So there's this pragma OMP target teams loop. This reduces your pragma complexity a lot. But it also leaves the compiler open to perform what optimizations it sees. So the compilers may not optimize this case as well as you'd like because it is fairly new. ROCm will generate an optimized target region implementation for AMD GPUs to use the Pragma OMP target teams loop instead of a Pragma OMP target teams distribute parallel 4 that we talked about in the previous slide. And you can get this with the -f OpenMP target fast option. So this is a compiler flag that will let you shorten those Pragma instances for AMD GPUs. Okay, and now the collapse clause. I think Johanna may have mentioned this one too. So for the collapse clause, it will collapse nested loops into one parallel construct. So what this does is it can just generate more work groups to help fill up the GPU, and you're going to saturate it with more work, which is good. Originally, only perfectly nested loops could be collapsed, so no extra lines of code between the for or do loops. Here we have an increment. But this constraint has been relaxed, and so now some lines of code are now acceptable, both before and after the loop. We can increment counters and such. And so this example, which previously would not have been collapsed, can now be collapsed with the ROCm LLVM OpenMP compiler and LLVM trunk. So if you have some situations like this in your code where you have some fairly simple additional lines in between the nested for loops, those should be collapsible. Okay, other compute clauses. So here we have a couple more: tile, num teams, num threads, thread limit, things that give you a bit more explicit control of what's going to happen. So for this tile clause, this is going to block your loop into small tiles rather than a standard loop traversal of all X and then Y values. So if you think about HIP tiled codes, this is what OpenMP is giving you, this flexibility to tile the loop. We also have this num teams clause. So this tells the kernel that you want to launch the kernel with the specified number of thread blocks. Num threads, once again, launch the kernel with the specified number of threads per each block. And then thread limit, cause the compiler to generate code with a maximum number of threads, which can reduce register pressure on, for some compilers are still adding this optimization though, so you might not get this in all cases. But these are things that give you a bit more fine-grained and explicit control over how OpenMP is going to launch the GPU kernels. And you might be more familiar with these if you have written like explicit HIP kernels before. But a great question you might have is, well, how do I even know what to set those, what to set values to? So this does require you to think about the hardware that you're running on. So this slide is just an example of something you might do, which is to understand your hardware options. Here we have opened our terminal window, and you guys can try this on the AAC cloud, and type ROCm info to see what information you are told about the MI300As I think you're running on. But here we see that for the GPU that we were running on, we had 110 compute units, a wavefront of size 64. So that's going to be down here, wavefront size 64. And then we have 4 SIMD lanes per CU. So SIMDs per CU, 4. So whenever we come up here and we are writing our code and we write Pragma, OMP, target, teams, distribute, parallel 4 SIMD, the options that we can provide for this construct, like num teams or thread limit, we want the num teams to be a multiple of some number of work groups with regards to the compute units that we have, right? We need to, we either want to schedule a work group to each compute unit or multiple work groups to each compute unit. And then our thread limit, our threads is going to be our threads per work group. And we want this to be a multiple of our wavefront size. So in our case, that's 64. And so now whenever where the kernel is invoked, we have this num teams times thread limit, and this should be a multiple or a divisor of the trip count of our loop, so the total there. So hopefully this slide makes sense, and it's just a deep dive into how the hardware can actually tell you what good options are to set for these. You also might play around with these in some of the examples or whenever you're porting code to see what gives you the best performance, right? Okay. So now let's move over to reductions and talk about those a little bit. So here, there's a lot going on in this slide, but we'll step through it, so don't worry. This is a simple example with a reduction, and you'll see this in the training examples folder. So we have some setup of our code. We're setting up our variables here, initializing them, and then we have the sum variable. Our sum is going to automatically set to 0 for sum reductions, so it does not need to be set for OpenMP, but it is needed for serial code compiled without OpenMP, so it is just generally a good practice to keep this here, even though you don't necessarily need it if OpenMP is being run with multiple threads. And also, just a note, scalars are implicitly first private in the target constructs. So we know that that the variable is thread safe automatically. Here we have pragma OMP target data map. So this is the data directive that moves data to the device or the GPU. Johanna mentioned this earlier. So we're moving A and B to the device. We have our compute loop on the GPU. We have a pragma OMP target teams distribute parallel 4 reduction plus sum. So the reason that this line above is red is because we don't need to set I to private. That's done implicitly for us, and we don't need to map sum to and from. Sum is going to be mapped back at the end. So here we perform our reduction, sum plus equals A, I times B, I, and then we can print our sum at the end. So this map clause should not be included if it is a reduction variable. This is the big sticking point here. Each reduction variable is initialized based on the type of reduction, and then the host version of the reduction variable is updated with the final result. And private I is also not needed because index variables are automatically private. This one you guys might already know because this is also true in CPU codes. And I guess a question is, well, why should we pay so much close attention to a reduction? Because they happen in a lot of applications, right? It's pretty common in physics applications that there's a really long computational loop, and then at the very end, you have to reduce into an array variable. Most of you are probably familiar with this, whether you work on weather encodes where the energy contributions are summed into ocean or atmospheric levels at the end, or you're going to work on something with reaction energies that are then summed into a particle array. And this happens in more applications than just these, but it is a very, very common case. Okay, and so what if we're reducing into array, right? I just talked about reducing to scalars, but the more common case is reducing into array. So the same as before, we're going to have some setup. We're going to allocate our now 2D arrays, A and B. But our pragma constructs and clauses are going to look slightly different. We still have our data directive to move data to the device or GPU. Now we just have 2D arrays that we're moving. And then we have our compute loop on the GPU where we copy the sum to and from the GPU and do a sum reduction on the variable. And here we actually have to explicitly say how many values are in that sum array. So there's going to be 2 versions of these reduction exercises that you guys can do at the end of this session. There's going to be reduction scalar and reduction array. And the only difference is that the first version obviously does a reduction on scalar variables, and then the array version does the reduction on an array with 2 dimensions. And I would encourage you not to just run the examples, but to open up the code and see what's going on, compare it against what's actually happening here, what I just said, having to explicitly map these variables with the different dimensions in the arrays, and see what happens when you change it, like what breaks. Because it's always good to see what's going to break a code whenever you're porting, because you're not going to get something right the first time, right? So we'll come back to this later with the exercises, but I definitely encourage you to play around with things. Okay, so here's some workarounds. What if your compiler of choice hasn't implemented array reductions yet? So some possible workarounds are to mark the reduction line as critical and use atomics. You could also separate out the majority of the loop as a pure parallel region and store that array, and then the second loop does the reduction one at a time with a critical region or an atomic. And you could also only parallelize the inner loops. There's a lot of things you can do to get around what happened if my compiler hasn't implemented this yet. And these are also things that I would encourage you to play around with, right? Even if our compiler does support array reductions, play around with these other cases, like what is the performance, or what happens if you decide to do it as only parallelizing the inner loop to do the 2D array reduction, things like that. Okay. Another common thing you might run into is device subroutines. So I would say most of us are not in the habit of writing all of our code in one gigantic monolithic file. And so we want to maybe call a subroutine or a different function from a target region. And so originally pragma-based languages required the inlining of subroutines in target regions. And so to call a subroutine from a target region, you had to have that pragma declare target added to the specification block, and if not visible, to the prototype. Okay, so that means whenever we have a function that's going to get called from an OpenMP parallel pragma region, we need to have these pragma OMP declare target and pragma OMP in declare target constructs around the function definition. You can also do this with data that needs to be declared on the target, but not necessarily move to and from the device, if that makes any sense. So you'll just surround that with pragma OMP declare target, pragma OMP in declare target. And not all, once again, not all compilers recognize device routines or can have difficulties with global variables that are used in these device routines. But the AMD OpenMP client compiler, this does work for them. And there's a couple of examples we have that show how to use this. Okay, so here's how it's actually used in practice. This could be global data in another file, object or common block. So we just have these constants that are set somewhere, and we've surrounded it with our pragma OMP declare target and pragma OMP in declare target. And then the compute is called from a target region in another file. So we still have all of these things with pragma OMP declare target around each one individually. So even if these two things were in the same file, like the constants and also the compute function, we would still need to put these clauses around them independently so that they could be called from the other file. And just a quick note on ROCm. So the ROCm and LLVM trunk are able to build device routines in the declare target blocks to be used from within the target regions. So there's also the feature of implicit declare target, where the following code would produce the desired effect. So here we have int foo, which is declared in the same file. And then we have our main function here, where we have a pragma OMP target teams loop. And then we're setting each value of a to be some data that was computed upon by this function. So foo will be implicitly made declare target by the compiler, because when building the call site in the target region, the definition of foo is available. But really what we care about is the definition of foo when it's in a separate file, which is what we have most of the time. So we would need these OMP declare targets and end targets around this function definition if it was to be in a separate file. Otherwise, we would get a linker error. And then I guess the second point here is that global variables are accessible from within declare target functions when using ROCm. So this is the device subroutine example I just mentioned. It's in the AMD HPC training examples folder, and there'll be another link at the end. It's in the same OpenMP folder that Johanna had mentioned, whether you're in C or Fortran. And so to build and run the code, just make this device routine. And we really do encourage you to try removing all of the OpenMP pragmas and then to do the GPU port yourself just to see what goes wrong. Because the tricky part is that all of the pragmas need to be added in both of the compilation units. And this becomes even more difficult with complex codes for both the programmer and the compiler. And I'm assuming most of us are going to be working on complex codes here, right? So if the device routine is using global data, it also needs to be marked to be available on the GPU. And so for using global data, you can see additional examples that we have in the folder, like device routine, W global data, to look at what that actually looks like. And yeah, look at the examples and have fun with them. All right, so next I want to talk a little bit about unstructured memory region directives. So just a quick review of data movement or management pragmas and clauses. We have the map to clause, the map from, which moves the data back from the GPU or from the target. And then we have the map to from, right? Moves the data to the target, and then at the end of the region, it moves it back. So these can be added to any compute directive. These are structured data regions, a block of code in a functional unit that will have data mapped over at the start and mapped back at the end. So we have a to and a from. But unstructured data regions are more flexible and can be done after array creation on the host and just before freeing the memory. So whenever you allocate the memory, you can have a pragma OMP target enter data, map alloc this variable name, and then at the end before freeing your memory, you can have this pragma OMP target exit data map release. So these are kind of the equivalent of allocating memory on your target and then freeing the memory and then releasing that memory from your target at the end. And obviously throughout your code, you might want to update these things or move them back to the host or device, or maybe you made some updates on your host and you need to make sure that the device or the target gets updated as well. And so there's this update clause that allows you to do that. So pragma OMP target update to will update this variable from the host to the device, and then pragma OMP target update from variable device to host. So you still have this kind of like fine-grained control over memory management with OpenMP if you need it. So complex cases. Usually the difficulty in porting a code to OpenMP is due to the complex combinations of codes, loops, functions, everything. So what we have to watch out for is structs and classes or any data type that doesn't map to simple arrays. All of the examples we've had up to this point have just been simple arrays. So allocatables, pointers, or implicit allocation, reallocation are tricky to get right, both for the programmer and the compiler developer. So the declare pragma can be tricky for both subroutines and data. And some variation and implementations also exist across compilers, just to add layers, right? So deep copies for things like structs or classes that contain pointers and data that won't be copied over to the device, or anything that has been added more recently to the OpenMP standard may have portability issues. So first we want to think about dynamic arrays that are dependent on the program input. So original code has so we can think about an original code that has a statically sized array, okay? We have this temperature array of a certain size. We have a pragma OMP target data, a pragma OMP end target data. We want to change it to a dynamic size based on input. So that we have just a pointer allocated to this temperature array, and then later we allocate the size. The malloc is going to assign a new pointer location to this atmos temp array, and instead use enter data after the allocation and preferably set values in a device loop. So pragma OMP target enter data alloc atmos temp with the size that we allocated here, size input. And so this is something just to keep in mind if you're going to have a dynamically sized array, because this is harder to catch in Fortran and C++. So what about dynamic arrays that are part of a struct and we have to think about deep copies, etc.? So here we have this pragma OMP target data and pragma OMP in target data just around our struct in general. We want to allocate the size of X, and then we want to do lots of code here. So there's some variation in current compilers on how they handle this release versus delete of the struct array. But OpenMP release has the same behavior as OpenACC delete. So this is kind of an open question, whether to use a release or not. But we think that the safest bet is to use a release. Okay. What about multidimensional arrays? There's more exercises for multidimensional arrays and arrays in general. If you go to the OpenMP examples and this Essentials of Parallel Computing textbook examples. So we just include those here. Those aren't maintained by AMD. It's not part of our HPC training examples. But if you need more complex examples, there's a lot out there, particularly in Chapter 11 OpenMP with a stencil code. There's also a Jacobi 2D OpenMP example in the AMD lab notes. And this code was written by some of our fellow colleagues. So definitely give this one a look as well, because it is another example of a more complex code that uses multi-dimensional arrays. So other options for multi-dimensional arrays might be MD-SPAN and C++23, which provides support for multi-dimensional arrays. You can write your program in Fortran, use a multi-dimensional array or multi-dimensional support library such as MATAR, a matrix and array library that supports dense and sparse data arrays that was developed at Los Alamos, and it works on CPUs and GPUs with HIP and CUDA. Okay, so we've talked a lot about data management and the idea of computing on things on a target device, but within the context of a host versus a target or a host versus a device. So what about unified shared memory, right? We now have APUs, so this is something we want to think about. Whenever we're using unified shared memory support, at the top of our program, we need to have a pragma OMP requires unified shared memory. That tells OpenMP, hey, we are going to use unified shared memory. We can get our device ID here, and then we can allocate memory on our target. And then we can use that memory in the parallel region. See, we don't necessarily have to do a map to or from or think about that very much. We just have a pragma OMP target teams distribute parallel for. We used we initialized the data on our host, and then we computed on it on our target region, and then we freed it at the end. We never had a map to or from. We never had an update after initializing and then performing our code here. So just to recap, we had an OMP target alloc for our arrays. We computed on the arrays or updated the arrays on the host and the target region, and then we had a free at the end without thinking about maps to or from. So OpenMP offloading with unified shared memory support. You can test out the unified shared memory example. It's Pretty straightforward, but you just set your target, your offload arch flag for you guys. That'll be the GFX 942, and then test unified shared memory. So I think the last thing that I wanted to go over before we wrap up this and give you guys some time for the exercises is the NWChem example. So NWChem was the code that was worked on by my colleagues. It's a computational chemistry software package. So they're doing some quantum chemistry and molecular dynamics. It's designed for large-scale supercomputers, and it was developed at the Environmental Molecular Sciences Laboratory at Pacific Northwest National Lab in the US. And so whenever my team was helping the developers port the code, they had to first find offload candidates. And so the offload candidates are going to be regions of the code that are compute intensive code regions, things that might port well to the GPU, things that are highly parallel. The compute scaling is stronger than the data transfer, so we can think compute is O of n cubed versus data, where the data size might be O of n squared. So traditional things we think about whenever what code will run well on a GPU or a high core count machine. Examples of this are Saxby's is a bad offload candidate because we have O of n data versus O of n compute. Unless the data is already present on your target device, then obviously a Saxby can be good. But a DGEM, or a dense generic matrix multiply, is a really good offload candidate, right? Because you're operating on n squared data, but it's O of n cubed compute. So there's a lot more compute that needs to happen versus the amount of data. So here's an example kernel, and they offloaded 27 in total, but here's just one. So all of the kernels have the same structure. There's 7 perfectly nested loops, and some kernels contain an inner product loop, so then 6 perfectly nested loops, and the trip count per loop is equal to tile size. So the tile size would be 20 to 30 in a production run. And with a naive data allocation, you could do a tile size of 24. So the per array transfer for each target construct is really high. They have 1.5 gigs of data being transferred host to device, and then 1.5 gigs of data being transferred device to host at the end. So as you might imagine, maybe copying all of this data to the device at the very beginning of a loop and then copying it back at the end wouldn't result in too good of a performance uplift, right? That's so much data to be moving around. So the first step was to reduce these data transfers so that we can actually see the benefits of computing on the GPU. So they did that by allocating these arrays once on the device, and then they stay on the device. And they're always kept there. The second thing that they did was they would update these 2 by 2.5 megabytes of data for multiple kernels. So these guys are allocated after some amount of communication, but then they're kept for multiple kernel invocations. So they were able to reduce that data movement overhead that would have happened if they had just done a naive porting of, let's move this kernel to the GPU and we'll move data to and from the device at the beginning and end. So after they've solved their data movement problem, now they need to do a presence check to determine that the arrays have been allocated in the device data environment already. So what that does is they just call this function here, which is a subroutine, and it makes sure that this data is mapped to the device. It's just a presence check. Okay. So invoking the kernels and the data management, this is something that you guys might run into if you're porting a really large scale code and you want to use OpenMP, but a really naive initial porting is giving you abysmal performance. we might think about things like this, right? Like how much data am I actually moving to and from the device? And it might be causing a much bigger overhead than is actually necessary. Maybe I should think about my data management a bit more. And so I'm moving less data whenever I actually call those GPU compute kernels. Obviously, there's going to be some codes where you do some amount of compute on the CPU and then do some amount of compute on the GPU. So data movement is inevitable if you're in a discrete CPU and GPU setting. But it's still important to think about which pieces of data can stay on which devices, right? Can this stay on the GPU? Can this stay on the CPU? Do I only need to update just this small amount to decrease that memory movement? And so in summary, AMD OpenMP compilers can offload computation to AMD GPUs. There's pretty good support for C and C++ and basic support for Fortran with active development underway, and you guys are getting to test out the flying new compiler now. And there's a really mature offload model with support for asynchronous offload and transfers. Maybe you can't do as much fine-grained work as you can if you were writing explicitly HIP kernels, but you can get pretty close. And it's backed by an industry language standard. So there's composability across programming languages. There's portability across GPU platforms for core OpenMP constructs. And with that, I will conclude with the link to the exercise instructions at the bottom. I think you guys are probably already on the HPC training examples GitHub repo. The Pragma examples main README has the intro to OpenMP instructions at the top. If you scroll down, you will see the advanced or real world OpenMP language constructs and then advanced. The real world OpenMP language constructs exercises are what correlates to the information I just gave you now. And you should also have access to these slides in the chat. So with that, I will leave it here and thank you.
Thank you, Shelby. That was a great presentation. So I see from the chat that some people lost access to the slideshow. I am one of those people, unfortunately. So I've heard from Juan that it may help to restart your browser or even change it to Chrome. So let's see if that solves it. Right now we have the exercises, and the next talk would be in 13 minutes by Samuel Antao for advanced OpenMP.
So it'll be 15 minutes, right? 10 minutes more.
Okay, so next up we have Sam, who will be talking about advanced OpenMP. Sam, would you mind giving a brief introduction about yourself?
Absolutely. So just a quick how to check. Can you hear me okay?
Yes, and we can see your blue pointer.
You can see the slides too and my camera. Okay, so hi everyone. Yeah, so my name is Sam Antao. I'm with the same department that Giacomo, Johanna, and Shelby are. So we are from the GPU data center department, and we work with users in the different HPC sites to help them make the most out of our GPUs. In my case, I work very closely to the LUMI supercomputer, so I lead the AMD effort around the LUMI Center of Excellence. Yeah, so that's pretty much me. I happen to have a compiler R&D background, but these days I end up working mostly around applications and application tuning. And yeah, today we have this talk about advanced OpenMP and trying to expand a bit more on what Johanna and Shelby presented before. Here the angle is more on, say, touching on a performance side of things. So there are different ways of doing things. There are different tricks that you can use to understand what different runtimes are doing. So try to cover that in this presentation, give a bit more of an advanced view on how to start thinking about performance. Can I go ahead, Jacob, or you want to wait another minute?
The stage is all yours. I cannot see the slides anymore, though.
I cannot see the slides as well, so that's a problem. So let's. Did I click something? No. Okay. So I see the right-hand pan. Something is happening.
There we go.
Can you see it again? Okay.
Yeah. Go ahead. Thank you, Sam.
Okay, so I'll put the pointer here. Hopefully I can scroll between slides. Yeah, so like other materials you'll be seeing this week, so this slide deck has a lot of contributions by many people, so thank you to them. And this is the agenda. I mean, in a way, we always revisiting some of the things we just talked about the concept of regions, about the management of memory, and also about the how to launch kernels. We'll try to add some extra sauce on the performance side of things and the different ways to go about this. So that's kind of the angle for this presentation here. Okay. Right. So as you know, when you want to port something to the GPU, there are like two main things that we care about. One is memory and data management. So basically how you organize your data so that it can be communicated effectively between the host and device. And also, how can you have your kernels consume that data in a way that is amenable to the GPU architecture. And the other part is the code execution. So basically how you actually going to express your parallelism, and this is the kind of the considerations we'll be discussing in this presentation. So usually, typically, you spend more time. You start spending time on the first one because it's kind of the hardest thing to come up from a CPU code to a GPU. It's like to think about the data, and then the code execution is is something you can do only when you start having data already on your device. It's usually the order things go. Right. So OpenMP has the concept of regions. So we talk about this in this last two lectures. And the region is basically a scope. So is where the pragma applies to. This can be area delimited with these curly brackets in C, or with the proper directives, like finishing with indirective in Fortran. So those are the region that the directive applies to, the pragma directive applies to. And we have these three kinds of regions: the data regions, the target regions, and the parallel regions. The data region is the region that defines how this data is going to, when it's going to leave, right, on a device, on a GPU, how it's going to be transferred. The target region is how some specific code is outlined to the device and executed on the device. And the parallel region is how you have, say, a given iteration space and you just chunk it so that you can work on it in parallel. The thing about this concept is that even though it was the concept that OpenMP Offload was developed with, this proved not to be quite suitable for do certain things, in particular if you work around object-oriented languages. So this is something that it's hard to map what happens in an object to some structure in your code. So you want to have something more that leaves you ability to do unstructured operations. And this is something that, again, Shelby just touched on this before, but is usually quite convenient that, instead of relying on these structured data regions, you want to rely on these unstructured data regions and instrument, say, object constructors and destructors to create an allocation and delete an allocation on your device. This is a convenient way that usually maps better to object-oriented coding, which is something that you care about. So I'm not going to basically spend much time on the details of the syntax here. I think this is pretty much covered before, and I'll just go over the memory management capabilities. And here is trying to discuss a few approaches on how you could choose to manage your memory. So the first one on the left-hand side is, I guess, the more intuitive one, where you say have a kernel, say a target region, and you want the data that is captured within that data region to be used on a device. So usually populate that with some map clauses to map the data to the GPU, or you may just want the compiler to capture implicitly some of the variables that are used in the target region, but the outcome is that you're going to have the runtime populating a table of pointers that keep this map between host and device. So there is kind of two instances of that same variable, one for each device that you're using, the CPU or the GPU. The other thing you can choose to do is to say, hey, well, I want the operating system to actually take care of my data movements. So I don't want really the OpenMP runtime do that. You want the operating system to do that. And you have this HSAXNAC variable. So this is basically saying that you want to use the ability of the link between the CPU and GPU to do the migration of pages between the CPU memory and the GPU memory. The outcome is it's not being very different in a sense that you're also going to have, a host, some host pointers and device pointers, and the two devices are going to control where is the latest version of data based on where the pages live. Right. This is one way to go about it. The other way is to basically say to the compiler using this prime OMP requires unified shared memory that, well, I don't want any sort of data movement to happen. This machine where this code is meant to run has unified shared memory, so the pointers that are valid to the host should also be valid to the device. And this is what you're going to have. You have only a single set of pointers that with the same address, and this address can be referenced on either side. So this is like a few ways that you can go about this. So looking a bit on the APU, so the APU is this not only this virtual shared address space, it actually has also a physical address space that is shared between CPU and GPU. And the exercise that we see that we want to do most of the time is to understand how can we use the APU properly and avoid copies. So I want to do some sort of automatic zero copy. And this is also showing you here 3 different ways of going about this. On the left-hand side, what is going on here is, again, leveraging the ability of the link between CPU and GPU to control the page migrations, HSAXNAC1, because one thing that is important to remember is that you have a physical memory, but still, the data is organized in pages, and each device has to keep record while pages is working on at a given time. So even though the data itself doesn't have to move, the information on the pages need to be, that some logic has to happen to enable you to do this. So the links, so this is still something you want to do, which is say, hey, link between the CPU and GPU, please make sure the page migrate properly. And then, if you have a normal OS allocator, a malloc, you can just use that pointer, and you may want to do this map to from, but there won't be actually any copies happening to enable you to use this X pointer. The other variant of this prime OMP requires unified shared memory, and this way just telling the compiler, hey, don't even bother generating any sort of logic to do these maps between the data on both sides. So I just don't need that. So you can just use this pointer directly. And there's a third way too, and this is when you disable the link between the two devices, HSAXNAC equals 0, you also build without support for XNAC, and you just telling the OMP runtime through this variable that you want it to, eagerly map things to the GPU. So basically, instead of using the OS, you want the runtime to take over and control these migrations. So there's like 3 different ways to go about this. I would argue that most of the time will be the one in the center. Okay, so next slide, please. Okay, so how can we go and optimize some memory between host and device? And here I will start picking up on the exercises we have for you for this lecture. So in a way, I may even go a bit over my time and go into the lecture because I think it's useful just to revisit the different exercises here as part of the presentation. But when it comes to the exercises, they are actually based in the same place of the previous exercises. So you just need to go to this GitHub link and clone it. And the other thing I wanted to tell you here is this very useful environment variable that is called libomp target _info. So libomp target is the library in Lang LLVM that is responsible to control the offloading to the device. And by doing this, you are telling it to basically be verbose about what it's doing, because a lot of things happen behind the scenes, and in a way you want to assert that the runtime is doing what you expect it to do. So it's very useful to set up this to -1. So it's like a bit mask. -1 means all 1. So you have all the possible information that libomp target underscore will generate. And let's take a look at the example on how you can interpret this output. Okay. Right. So just a quick summary. Just a kind of a recap of what we discussed in the previous presentation. So when you manage memory, we have different ways to go about this. There are different clauses to control it. So one is this map to and from. So what this does is to assess if there is something related to that variable already allocated on the device. If not, he allocates. And then there is also this notion of reference counter. So if you have nested data regions, so there is always the outermost that is going to prevail. So whatever you decide to do on the clause of the outermost tend to prevail. And the way this is controlled is through this reference counter. So each time you get into a, say, innermost target region, this ref counter is incremented for the different variables that are captured. Right, so this is something that is going to change when you map some data as part of an OpenMP directive. For this particular case, to the to and from, he is going to copy the data. If this ref counter is not 0, he's going to copy the data to the GPU and from the GPU, depending on how you use it on your using your clause. The other options here is to use a lock or delete. So this is about making an allocation available of your device and also manages this reference counter, but it doesn't copy the data, right? Just creates or releases the allocation. And release is actually the third one, which makes it make this this deallocation on the device to be dependent on this reference counter, right? So when it gets back to 0, so if you get back to your outermost region, that's when the data is going to be released and doesn't do any copies. And then there is the third one, which is about making the copies with assuming that the allocation is already available inside your device. So this is basically a quick cheat sheet of the different clauses you can use to control your maps and update the data on your device. Okay. All right. So let's take a look at the first example. So this example that we have for you and the exercises around this lecture here are built around this DAXP code. So there are like a few things to it. So here we have the location of the arrays, some initialization, and then there is a loop of multiple iterations where the DAXP function is going to be called. I wanted to just hint here already that usually when you want to use GPUs with pointers obtained from OS allocators, you may be willing to adjust a bit the alignment. So it's more amenable to the caches the GPU have. So this is usually a way to get more performance, but I'll get more into this. But I just want to make sure that, I just want to get to the first example, and that's, that should be the way to go about this. There's, more to be, but I'll do that on a later slide. But going back to our DAXP function here, so we go to the next slide here. Well, there is some accounting of the times and making sure the results are correct. But this is the main kernel that will be running on these exercises. So there's a big long directive, OMP target team, just with RHEL for SIMD. As Shelby just said, SIMD can be lifted for the client compiler. This is really not needed. It's just been there. It's something that was being used for some of the compilers, but it doesn't do any harm to leave it there. So basically, this is the code that we are running. We are having this directive here, and we have some maps to control where the data goes. So if we now run this, and because we cared putting this label MP target info variable on our environment, we see the runtime just spitting out a lot of information, right? So one of the part of the information that you get out of this is about variables that have been mapped implicitly. So if you remember, so let me go here. Just very quickly, like in the previous slide, so you see there is, the main arrays, but there's also a scalar A, there is also a scalar N. So there's like a few things that is always captured implicitly, and you can use this, this trick to tell you what were those, right? And this was N and A that were captured implicitly, and they were marked first private, meaning they are private for each thread, and each thread private instance was initialized with whatever value they had before the target region. So this is the first thing. The other thing that is going on here has to do with the creation of the maps between host and device. And this is what you see here. Create new map entry, and it tells you the pointer of the target data that was being allocated for this map, and also tells you how the management of this reference counter is happening. So we are entering a region. This reference counter has been incremented to 1. If your clause set to the device, then you also see that there is some copying being done from this host pointer to this target pointer of this size, and this happened to be the name of the variable. And the same thing they show this for X, they show this for Y. So you see all this information here. Then this is followed by the actual issuing of a GPU kernel. And what the runtime is going to do is to make sure that for each piece of data that is captured inside your target region, there is a map, right? Some of them were, and all of them were kind of created before, and this is just being summarized here to tell you, that this data is available on GPU, and these are the target pointers that I'll be using for my kernel. And then after my target region, kind of an opposite, the reverse mechanism happened for Z. So there's copy, out of the device to the host, and the different maps are just removed. So this is like a way to interpret the output from libOMP target info. Okay. Right. So the other exercise that we have next was to replace the structured data regions by these unstructured data regions. So you'll see, that we have this OMP target enter and target exit pragmas that basically define the boundaries of this unstructured region. And this is what happens in your libOMP target info report. Is pretty much similar to what you see in a structured region, except that it happens at the point where these pragmas are met by the main host thread. So creating a new map, then you see when you go to the loop, you see the map already exists. In this case, because it was mapped before, the ref counter now is 2, because there is an outermost region that is controlling the mapping of that specific data. And then when you delete data, the reverse happening, and the ref count goes goes back to what it used to be. Okay. Okay, so this is about you may want to have an outermost region, but you may want also to update data on your device. And the way to do this is by using the update pragma. And this is how it shows in LibOMP target report. Basically, you see this copies of data happening and the checks that the maps exist. Right? This is pretty much what this example does. Like moving on to the next example, this is about discussing, when you close your unstructured data region, if you want to use a delete or if you want to use a release. And I mean, this usually depends on your application. I mean, if you know that your data is never going to be used after that point, delete is usually recommended. If you want to rely on a nesting of the region, so in this reference counter, so then you should use the release. I mean, there is really no right or wrong here. Is whatever makes sense for your application. In this case, would be irrelevant. But both will work. Okay, so from exercise 7 onwards, we start to explore this unified shared memory. And the main change is this pragma that you have on the top of your compilation unit, which says, hey, this compilation unit is to be built for a device that has unified shared memory. So if you have target regions, don't care, trying to generate these maps. So what you see coming out of this libOMP target info is that all this logic about the maps, all the copies, they basically don't show up there anymore. So this is managed by the operating system and not by the runtime anymore. You may choose, in some cases, to be backward compatible with a device that may not have unified shared memory, so they want to keep your maps, but you'll see that it won't make much of a difference. It's like a subtlety I'll discuss towards the end of this talk, but there won't be any difference between keeping the maps because the data has been again managed by the operating system, so there was no copies whatsoever that are being shown up by the libOMP target report. Right. So the other thing that this unified shared memory is useful is to basically make deep copy easier. Right? So if you use an object that has multiple pointers inside, or that contains multiple pointers, so you want to be mapping each individual pointer, like a very common case is the standard vector implementation. So it keeps a pointer to its storage. And it's very popular, right? So it's been very pervasive around the different codes that we come across. So by using unified shared memory is actually something that really makes it easier to use this sort of vectors because the deep copy case is much better covered. This is just a hint on other exercise that there has been not only vectors, but there's been this val array containers part of the C++ standard library. So this is something you might be interested in using, and this in this case is safe to just map the object without the deep copy. So again, you may consider using this sort of containers for if you care about some backward compatibility for machines that don't have unified memory. Just to close this part about the memory regions, just sometimes if you just activate this variable, it can give you a lot of output and sometimes maybe hard to navigate. You may want to limit that by taking advantage of this kind of hidden runtime call that is provided by the OpenMP target runtime, where you can enable for specific sections of your code libOMP target to dump all this information. So you have a bit more tailored output for what you want to investigate. Okay. So now this next section is about optimizing memory bandwidth. So basically, I have a kernel. There's some data there. How can I get good bandwidth from my GPU memory? And this example here, stresses this part. I was already touching on it when he started the exercises section, which has to do with alignment, right? So this is the similar code that we were looking at before. There are a few variables with the difference that here I'm actually controlling the alignment of the allocations. So I'm still using DOS allocators, but here I'm defining specific alignment for each one of them. Because if you don't do anything, it's usually 16. We're doing up to 128 bytes alignment. And here on this table on the bottom, I'm showing you basically the bandwidth that is achieved for different different variants of this implementation here. So one uses only up to 128 threads with OpenMP, another one with OpenMP up to 1024, and also a plain HIP implementation. And here I'm on this the top of the table here. I'm just changing. Actually, a bit dark. Some apologies for that, but I hope you can see. We are changing the alignment. What you can see this is as actually quite dramatic implications when it comes to performance. So we typically recommend that you use 128 or more alignment so that you could actually get some good bandwidth. So 128 is the cache size of the MI300A, so there's something related to that. But this usually want to be in this space here to really get good performance out of your memory link. Just a comment here, you may be willing in exploring some compiler options that allow you to tune this alignment in case you don't want to be instrumenting your code with this alignment. So there are some options at compiler level, and also you can have other tools that, like the POSIX memory line is one of them, to control the alignment of the pointer. So just something to bear in mind. Okay, so this is like the example that we're looking at before with this, with this improvement here that controls alignment of the pointer. So it's pretty easy to do. Not really has to change. So just the alignment of that pointer there. Okay, so this is pretty much a summary of what I just said. More than 128 or more, that's usually what we might be willing in using. If you have mallocs in your code, just considering using this POSIX memory line and basically different mechanisms for you to control the alignment and get better performance out of your GPU memory link. Okay, so that concludes the memory optimization part. So now we're going to look into kernel traces and its optimizations. Exercises are in the same place, except that instead of memory pragmas, now we have kernel pragmas. And we're going to also use this this variable here that is provided by that is interpreted by the OpenMP runtime to give you information about the kernels, in particular how they have been, are they being dispatched to the GPU. There's just like a quick comment. I mean, some compilers, have their own ways to do these similar things. Like, so this Cray compiler has this Cray act debug, which will, do similar things to this libOMP target kernel trace. So something, if you use a different compiler, just explore the options they have there. Okay, so this is like the first example, and what you'll see if you specify this variable here is the dispatch information for a given kernel. And interesting things you may be willing to interpret here. First is the number of threads per block, the number of blocks, but also the resources that it uses. In particular, when it comes to the local data store, and the registers, right? And more importantly, if any of these registers are actually being spilled, because this is usually impactful on a performance. So you should most of the time be trying to avoid register spillage, because you're just doing more memory transactions that you might not need if you just tune your code so that registers don't have to be spilled. Right. So what we experience here on this exercise is try to start some adding clauses to control the number of threads, and I wanted to basically give you like a very important nuance here. So there's this clause that tells the compiler, actually we used to tell the compiler that you want to run on a specific amount of threads, in this case 64. If you do this, you can actually see the 64 size being used here, but you actually don't see, because you specified less threads, and by specifying less threads, you think, well, maybe there'll be more resource available for each one thread, so I'll need to spill less. But what you see is actually doesn't make much of a difference if you just do num threads. So instead, and looking at the other exercise, you might be interested in setting the thread limit, because this is actually what is going to be translated into what you call a launch bound for your kernel. So it basically tells the compiler that you will never be willing to issue this kernel with more than 64 threads. And because of that, you'll be able to use a few more registers and avoid the spills, right? So this is one of the procedures that you can imagine yourself doing when you are optimizing your OpenMP kernels, taking a look at what is being spilled and maybe adjusting the thread limits just to allow each thread to be able to use more, local address or more registers. Okay, so this is like just a summary of what we talk about. I mean, this example is very simple, so it's not like performance-wise will make a big difference, but you see, really there is some changes coming from the number of registers by using thread limit that doesn't happen if you just set num threads. It's basically the message that I wanted to convey here. So this slide here is just to tell you a bit more of information about how should you interpret the amount of resource that is acceptable. So how can you calibrate your expectations in terms of performance for a given amount of resource that is being used by your kernel? So one thing that is useful to understand is that GPUs execute your kernels in what you call waves, and we have 4 execution units in each one of the compute units. So that means that I can have 8 times 4 waves going at a given time in my compute unit. So say if you use very few resources per thread, you can allow yourself to be in this space, or you have most of or all the waves that are possible to be running on a compute unit at a given time. The moment I start using more resource, it means that the schedule cannot issue all the 8 waves, and your occupancy of the compute unit starts decreasing up to a point where you can only have 1 wave. And if you use even more resource, then you need to start spilling, right? So this is going to really decrease your performance, right? So really, we should try to be as much as possible here. But if not, because your kernel is has a lot of complexity, you just want to calibrate your your compilation with a sensible number of threads to make sure that allow you to use more resource without starting to spill. Right? This is kind of an important thing when you are optimizing particularly fairly large complex kernels. Okay. Yeah. So, well, I guess in a way this was already covered by Shelby. So I'm going to just go over this very quickly. I mean, this is kind of a wordy pragma, this is not needed anymore. We know they can replace this with loop. There's kind of new ways of doing this. It's just giving you a bit of the story behind this. So I'll leave this slide here for you to look at later. I'm just going to very quickly move on. Some resources that you might find interesting for your work is the resources about the different tools, AOMP, IPFort, which are things we see usually integrated alongside your OpenMP code. So something to keep on your toolbox. Okay, so this is the last part of this presentation, and it's going to touch on atomic. And this is something that applies to the MI200. Everything else that I said up to here, pretty much apply for both MI200 and MI300A. MI300A is this ability to you don't have to actually be sharing, copying data between the device, but everything else in terms of the kernels, the registers, everything is the same. But there is some nuances about floating point atomics for MI200 that we think is important to communicate here. So this is basically what we have seen before. When you want to assess what is going on with your code, you compile with Clang, you control the architecture, you may be willing to set this HSX SNAC1, and there's also these variables here to understand what's happening and what the runtime is doing for you. Right. So this is kind of what we can use. And depending on what you are, the different options that you choose, you may be getting different sorts of memory. So there is this notion of coarse and fine-grained memory when it comes to MI200 GPUs. And the main difference between the two is that for the coarse-grained memory, you can only expect it to be coherent on a synchronization point, right? Whereas the fine-grained is a memory that is always coherent. You can even have it made coherent within a GPU kernel. So this is useful if you want to same data being touched by multiple devices or between the GPU and the CPU. So there's a mechanism, if you have fine-grained memory, that makes sure this data is made coherent. Most of the time, you want to be using this coarse-grained memory just because it's optimized to avoid coherence what is not needed, or just do it when it is needed, right? Something that I wanted to clarify here. So how do you get these different sorts of memory? So typically, when you have a target region, and you map your data from the host device by using these clauses here, you get coarse-grained memory. Right. So this memory here is just a new allocation that happened on the device made by OpenMP runtime, so it's made coarse-grained. If I don't do the map and I just rely on unified shared memory parameter right here that says, hey, I want to use the same pointers I use on a CPU that I allocated using my OS calls and I want to use them on my kernel, what you're going to get is fine-grained memory. So the memory that comes out of the OS allocators are fine-grained. But this will work because you have unified shared memory, and this is supported. So one thing that you can do is, even if you at some point work with fine-grained memory, you may want to eventually enable your maps so that you switch to coarse-grained memory. So this is a possibility. There will be more copies done, but at least they allow you to, so by keeping unified shared memory and adding the maps, a way for you to keep the original allocations, but having it being coarse-grained memory. So one of the things that important to note here is that the moment a piece of memory becomes coarse-grained, it is going to be coarse-grained for life. right? So the other way around is not going to happen. So the moment we map it first, so say here there was still fine-grained memory. I do the first map, it becomes coarse grain, and then I'm not mapping things on some following up target region, but here the data is still going to be coarse grain because of some previous map. So it's kind of a sticky feature of the yeah, it's pretty much what I'm representing here on this slide. Okay, so these are kind of the details. You know, so if we do a map clause, there is a device allocation and some transfers. It's going to be coarse grain. If I use a map, unified shared memory is going to be coarse grain as well. If I use OMP target allocation, so the API calls, is going to be coarse grain. And it's also the locators for pin memory, which is not really what we're discussing here. Now, and the reason I'm telling you all this story here is because this has quite important implication when it comes to atomics. So it's important to understand what are the currency points of a given piece of memory so that these atomics do work, and do work in a way, you know, that are performant for your application. So one of the things, you know, this basically showcased something that will fail if you don't careful with this sort of thing. There is this hint that we can use, and also some compiler options that say, well, I want the compiler to emit what we called fast floating point atomics. But what does this mean? It means that these are atomics that are implemented at the level 2 cache of the GPU. So they you know, you don't need to go poke at what is happening around all the other devices on the CPU to see if this piece of data is being touched. No, so you're just saying is enough for, you know, for me to, you know, materialize the atomic at the L2 cache within the GPU that I'm working on at a given time. So the way you tell the compiler to do this is by using these hints, and also some compile options. So if I have fine-grained memory and I do this, this is not going to work. It's going to basically be, you can get wrong results out of this. So how do you fix this? So one of the ways you can use to fix this is to add a map clause. If you remember, if I have some fine grain, the moment it's mapped, it becomes coarse grain. So I can then use this fast implementation of the atomics. So this would be a way to fix this part. Another way is to change my hint and say, well, I'm okay not having this, you know, fast implementation of my FP atomics, but I want it to be safe. And this is going to result in implementation that uses a compare and swap to implement these atomics. So it's much lower performance than the fast FP atomics variant. So a summary of these different combinations you can have here. So if, you know, by default, if you don't do anything, you know, the compiler actually always tries to be on a safe side. So it's going to, by default, if you don't give any hints, you don't give any specific compiler options, to use a compare and swap loop to do the atomic. Then if you want to activate unsafe atomics, then you can start, you know, having you know, the implementation to opt for them, or you could also, you know, set this hint as part of the OpenMP implementation, and this part here is going to really, you know, take advantage of this faster implementation. The moment you want to be safe, and you know, you can pass the hint, and the hint supersedes the compiler option. Is going to, you're making the compiler to opt for a compare and swap loop to implement your atomic. So if your application is very heavy on atomics, this is, you know, tremendous implications, and that's why I wanted to, you know, to be aware that it's quite important to understand what is this concept of and of course radius. And I guess this is it. Just a quick conclusion. And one thing I want to note here. I mean, OpenMP is a standard, but there are specific behaviors that are specific to a given compiler implementation. So it's something to bear in mind. To remember this SIMD directive being needed on this very long pragma. So there's one of the things that may differ between compilers. So just bear in mind that this OpenMP implementation is always kind of a moving target. It's always being optimized. We try to understand what is more beneficial to the users. Just bear in mind, that's important to know. If you come from a different compiler, you may have to calibrate yourself a bit to say the AMD compiler implementation. Well, similar things goes to this course fine-grained memories. This is still something we are working to optimize and do better and pick better defaults. So if you have feedback on this, we always be happy to learn from you. What are your use cases and what do you think could be helpful for your use case? And with that, this is kind of what I wanted to have for you today. So the slides are on the same place, and you could maybe use the remaining time just to go over them. I kind of just cover pretty much the exercises here, so it'll be good for you to just to go and with more time, step by step, see what are the different directives being added, being removed, being changed, and see how it translates into the runtime behavior. Yeah, so that's it. So I don't know if Giacomo is on.
Thank you, Sam. Yeah, that was
a
great presentation. Yeah, so as Sam said, you can go ahead and try testing out the exercises on AAC. The container is up and running, and you can use it even after we log off. So let me just take the chance to thank our speakers today for delivering great presentations, Johanna, Shelby, and Sam. Thank you for your availability. It's always great to hear from you. And also, I'd like to thank the people in attendance for your interest and for interacting with us. We are very interested in hearing your opinions and requests, and we're very eager to work with you. So yeah, for tomorrow, we have HIP and OpenMP and HIP interoperability. We'll keep monitoring the chat today for a few more hours, just in case you need anything from us. And please send me a message if you have still issues logging in, but I think that maybe 95% of the people should be all good looking at the last log command from the container. So yeah, with this, thank you again, and we'll see you back tomorrow. And also, let me thank Juan for being the manager of all this and keeping us all in check. Thanks a lot, Juan.
No problem. Thank you for providing this course. It's been very helpful, interesting.
Okay, thanks everyone. We'll see you tomorrow.